In this video, I will be showing you some inside bobbin probe signals on the Staveley Workstation 2000. This is actually a dual frequency tester, so that qualifies for multi-frequency. Although most modern testers can run 4 frequencies, 8 frequencies. It just depends on how much money you want to spend on a tester and how advanced of a test you want to perform. I mean, if you're running array probes, you're running a whole bunch of channels and probably more than 4 frequencies. Okay, so the first thing I'm going to do here, I've already set the phase on my calibration tube flaws. So what I have in here is, on this end, there's 3 wear scars. So these are simulated structures, support structures from the heat exchanger. And I got a tube support ring, then I got a 420s, 90 degrees apart, then a 60% hole, and then 100% through-hole hole. So I've already set my rotations. So let's watch what happens when I move the probe through the tube. First, we see the 20s going, they start up first. And then we see the 60 starting up first. And then we see the 100 starting up and to the left first. Now, anybody that's done tubing exams knows that, at least in the US, that's upside down. Now, the reason it's upside down is because I pushed the probe in. And you always record data on the pull because that gives you a more consistent data acquisition rate. You don't get as much variability in the pull speed. So now I'll do is just erase my screen, renull. And then I'm going to slowly pull it back. Watch what happens to 100% when we record on the pull. Down and to the right. Now, normally we set that to 40 degrees, but today I chose to set noise horizontal. You got to do whatever your procedure tells you to do, but if your data is real noisy, it's common to set it down to the noise horizontal, clean your strip charts up a little bit. And there's going to be our 60% hole. And then we've got our 420s. You only see one signal because bobbin and encircling coils average the whole circumference and give you one output, one signal. So here we can see a probe wobble's horizontal, and something right at the ID surface would have very close to 0 phase lag. But the 100%er, the reason that that's the signal's at 40 degrees, the weighted average of your eddy currents are going to predominantly be more towards the ID like this, because that's where your eddy current density is highest. And they're going to have the most input into your output, which is that signal. Then we get quite a bit of phase lag for the 60% OD flat bottom holes, because eddy currents don't get disturbed until they get quite a ways through the tube. That's why you get a lot of phase lag for the 60. And the 20%er, I'll just renull just to get her back in the middle. The 20%er has even more phase lag because they're even further away from the probe, right? So now you've seen phase lag on one channel, but what's nice about the multi-frequency, and this tester can do multi-frequency. There we go. Now you can see how the phase lag differs between 2 different test frequencies. So now I'm going to go back into my tube and hit null and then hit erase. I don't know if you've noticed it or not, but my first channel is 360 kilohertz, second channel is 180 kilohertz. So if you just think about what's going to happen before we acquire the data, lower frequencies penetrate to deeper depths quicker, so you have less phase lag. So if my 420s are over at this angle on a higher frequency, they're going to be something like that on a lower frequency. So first we go past the 100. Now watch what happens when we see the 60s. The one on the right is going to have less phase lag. See that? A lot less phase lag. The 60% flat bottom hole is straight up and down on channel 1, but it's about half that phase over here on 180 kilohertz. And then when we go past the 20s, they're about 155 degrees over here on the first frequency, and on 180 kilohertz, they're about 88 degrees, 87 degrees, something like that. So what this tells you is that OD pits rotate counterclockwise as you lower the test frequency. If I had any ID pits in this cal tube, you would see the opposite. As you decrease in frequency, shallow ID pits would rotate up towards the 100% signal. Now the last thing, let's just look at signal amplitude. I'm going to go past these 3 wear scars. Now these are large volume flaws. That's going to be the tube support plate there. We don't care about that at the moment. What we care about is these 3. All right, that's going to be the first one. I just noticed something. This whole time, I had 180 kilohertz upside down. Did you notice that? If you noticed it, why didn't you say something? So what I have to do, is that going to be about 180 right there? We're going to find out how good I am. All right, there we go. Tube support plate. Now these flaws are going to start down on both channels. See that? That's going to be a 20% OD wear fretting flaw. Notice the phase of those two is not dramatically different. But look what happens when you go to the next bigger one. Now there's a little bit of phase between the two, right? Between the two frequencies. But if you look up one particular frequency, for example, this 180 kilohertz, look at the amplitude difference between the 20% flaw and the 40% flaw. It's over double the size. But there's not a ton of phase difference on these larger flaws like this. So what that tells you is that when we create sizing curves to size large volume wear scars like you get at tube support plate or AVB wear locations, instead of using a phase versus depth calibration curve, we use amplitude versus depth. So we say, if you got something that's small like this, it's 20 volts. If you got something that's double that big, it's 20% or 40% deep. And then watch what happens when we go to the 60. Even bigger still. So we would set that as our third point. So our calibration curve, once it's all set up, when you would see something like this and you'd measure it, it'd be 20% because of the voltage amplitude. When you see something that size, you would size it and it would say 40% based on the amplitude. And then finally the last one, big amplitude difference. When you measure that, it would come up as 60% based on the large signal amplitude. All right, so there's multi-frequency testing on a 2-channel Staveley Workstation 2000. End of video.